Hello world, my name is Victor Engelmann, and in this video I'm going to explain context-free grammars to you. Now, in a previous video we've talked about regular expressions, and I absolutely love regular expressions if you haven't figured that out from that video. But regular expressions have some shortcomings, so they are quite limited in some ways. And if we are talking about parsing a programming language, for example, one of the shortcomings of regular expressions is that they cannot be recursive, in the sense that, for example, if you want to describe a function call, for example, a function call can have parameters, and the parameters of the function call can also contain another function call, so that you get the result of that function call as your parameter. And what that means is a function call can contain a function call, or similarly a statement can be, for example, an if then else, and the block in the then or else case can contain other statements again. So statements can contain statements, or arithmetic expressions like the cosine of 1 plus 1. Okay, so the cosine is an arithmetic expression, and it contains a 1 plus 1 as a parameter. So arithmetic expressions can contain other arithmetic expressions. So an obvious thing that you might want to do is just take regular expressions and add recursion on top of that. And if you're reading books about programming languages, then you might see something similar to an automaton that we've talked about, where you could have something like an identifier, if you're describing a function call, then open parentheses, and inside these parentheses you can have something like, either nothing. You could have a function call without any parameters, and then you're done. Also a semicolon. But then in there you could have something like a number, for example. Okay. Or you could have another identifier, for example, if you pass a variable to your function call. Okay, so far this is all still doable with context-free grammars, but this is also still doable with context-free grammars. So you could have a comma in between and then another parameter, although this would allow you to just have a few commas. Programming languages don't necessarily forbid that, but anyhow. The interesting part is now that this is a function call. Okay, and then you can have down here, and that's usually with a different shape than these atomic things here. You could have another function call down here. Okay, so that could be something that you could see in a syntax diagram in a programming book. That's not uncommon. But when we are talking about parsing a programming language, then this approach has a bit of a problem because when we parse something, then we want to get something out of the parser, right? So we want to read our input and then get maybe some object that is composed of a list of instructions, for example. So this whole thing should have something like a result, which and when you construct that result, you would like to have access to the value that you get from this recursive call here. And this approach doesn't really make sense in that context because, if you have multiple function calls in here, how are you going to identify the function calls? Just doesn't make sense. So a different approach now a different way to represent the same idea are context-free grammars. In context-free grammars, you have such a start symbol, and then you have so-called productions, which allow you to replace some symbol on the left-hand side with a sequence of symbols on the right-hand side, like A, B, or B, A, for example. A might go to A, B, or C. B to B, A, or I don't know, B, D, A, for example. D is sufficient. Now, if you have your start symbol and your productions, then you can you start with your start symbol, and in every step you take one of these left-hand sides and replace it with the right-hand side. So you could take that S and replace it with A, B, and then you could replace that A by A, B, B. You know, this first A is this A, this last B is this B, and this here is the right-hand side from here. And now let's replace that A with a C. Okay, and it's customary to draw this with a in a tree shape like this. So you could draw this like this: A, C, B, B. Now this C comes from that A, so you have that A. This A, B comes from an A. Okay, so so this gives you kind of a tree that contains all the information about how you went from an S to this final text here. And this is all a bit theoretical at this point. I always prefer to do something with a more practical example for context-free grammars. As I said, they are very useful in the context of developing a programming language. So let's say your start symbol is an S, and let's say that represents a statement in a programming language, then something that you might have as a right-hand side is an assignment, like identifier for a variable name, for example, equals an expression, semicolon. That could be a statement. You know, you have some arithmetic expression and you want to evaluate that and then assign it to a variable. Or you could have as a statement if open for open parenthesis, b for a Boolean expression, close, if Boolean expression statement. Okay. Or you could have if open b close s else s. Okay, so you have an if with a Boolean expression that you are testing, and if that gives you a true, then you execute this statement, otherwise you execute the statement that you get from here. And by the way, compared to syntax diagrams, this has the advantage that you just have one sequence of things that you can get, and then you can take the result from here and here and here and construct an object from these, and you don't have this circularity inside these cases here. Or let's say you could have while open Boolean expression close statement. Okay, now what could be a Boolean expression? A Boolean expression could be true or false, or a Boolean expression and another Boolean expression or another Boolean expression, not Boolean expression, and then something that you would often see here is reference to a relative operation, like A less than B, or B less than A, or A greater than B, stuff like that. So a relative statement or a relative expression could be an arithmetic expression less than another arithmetic expression, or an arithmetic expression greater than an arithmetic expression, and so on. Okay? And yeah, then the arithmetic expression could be a number or an identifier, so you could take a variable name here, so you would want to read or take a value from a variable. So an identifier could be an arithmetic expression. Then you could have an arithmetic expression plus another arithmetic expression minus an arithmetic expression, and so on. And that already defines a huge part of a programming language, except right now we can only have one statement. So we might want to have a different start symbol. Let's call it T. And with our T, we might want to generate multiple of these S's here. because a program has multiple statements usually, right? So we would have something like t goes to either nothing, epsilon, or to ts. Okay, so and with that you can just start with a t, and from there just generate any number of s's. And then at the end replace that t with epsilon, so nothing. So now you have SSS, and each of these s's could map to, could then bind one of these statements here. And if you are thinking in the direction if then else, this statement here can be a block again, right? So you would also have a case like open braces t, because you can have multiple statements again in there, close braces. Okay? And okay, this is a primitive language. We don't have arrays or functions or classes or something, but this already defines a Turing-complete language. Yeah, that's not bad. Just a few of these lines, and that already defines something Turing-complete. That's not bad, if you ask me. You know, again. Let me emphasize a few things. These identifier equals, semicolon, if, open, close, else, while, open, close, open braces, close braces, true, false, and or not. Less than, greater than, number, identifier, plus, minus. These would be the things that you would get from the Lexa when you are writing a parser with Bison. So if you were to pass something like I don't know, we set x to 5, and then if x is greater than 0, y equals 1, else y, set y to -1. So a little program that just computes the sign of x. If we parse this with this context-free grammar, then we could get something like this. Again, t goes to ts, tss, ss, and now this ss would go to identifier equals an expression, semicolon. This expression goes to number, namely 5, namely x. And this s goes to if, open, boolean, close, s, else, s. This boolean goes to relative operation, goes to e greater than e, this expression goes to identifier, namely x. This expression goes to number, namely 0. Okay, this statement goes to identifier equal expression, semicolon, and this identifier is y. This expression goes to number 1, and the space gets a bit tight here. So the same thing over here. This s goes to identifier equals expression, semicolon, identifier y. Expression goes to number -1. So okay, so this is the parse tree of this source code relative to this context-free grammar. And if you have this parse tree, and with Bison it's not so hard to get from here to something that will give you this parse tree, then you can obviously see how you can then run through this tree in a recursive manner to generate code from these things, or maybe not even generate code, maybe just interpret the things and execute them in something like a virtual machine or so, or a programming language interpreter. By the way, this thing here is called an abstract syntax tree. If you go in the direction of compiler construction, that's a very common term that you will see all the time there. So this is already a pretty good first approximation for a context-free grammar for a programming language. I want to finish this video with some practical advice for your design of context-free grammars. You've seen that I had this rule t goes to ts. Okay, you could just as well have t goes to st, and that would also generate the same sequence of s's. And having something on the left hand side and then also on the left of the right hand side. As programmers, we should panic at this point, because this looks like we are getting a stack overflow, but the developers of Bison actually advise you to use this left recursive version, because that just requires less stack space. So when you do it like this, you only need a constant size stack, and like this you would need a linear size stack. So that's just better in terms of the stack space. Then let's talk about operator rank. We have here arithmetic expression plus arithmetic expression. Let's also have arithmetic expression multiply arithmetic expression. Now, if you have something like this, and let's say you are now trying to parse 5 plus 3 times 2, well, the multiplication has a higher rank, so you would assume that it should be parsed like this, and then you should get 6 plus 5 is 11, right? But yeah, if your grammar looks like this, yeah, nobody guarantees that. It might as well just parse it the other way around, so 5 plus 3 times 2, and then it's 8, 16. Okay, and obviously that's not what you want. You want your programmers to get what they expect, and since multiplication usually has a higher rank than addition, you want to respect that, so that your users aren't surprised by such a stupid behavior here. Yeah, tools, compiler generators usually give you some way of saying, of defining a rank between the operators, but I don't think that's such an elegant way to deal with it, especially when your grammar becomes big and complicated. Then stuff like that can really get out of hand. So I think a better way of doing it is like this. You have E goes to E plus E, or E minus E, and then you have another level, so E can go to E2, or let's call it M. Okay, and M goes to M mult M, or M diff M, or I like to call the next level X, and X then goes to number or identifier, or, and that's the trick now, you can have open parentheses, open, then you are allowed to go back up when you put it in parentheses. Okay, open E, close. And yeah, that's just a neat trick that forces the corresponding program to yeah, to associate these things first before they are pushed further up the tree. Okay, so that's how you can deal with operator rank. But if you do it like this, you get the next problem. When you do it like this, E goes to E minus E. Yeah, what if you want to pass something like 6 minus 2 minus 3, for example? Normally, programming languages are left associative, so if you're parsing this, it should be interpreted as 6 minus 2, 4 minus 3 is 1. But if your grammar looks like this, then yeah, your grammar is free to parse it like this. E goes to 6 minus e 2 minus 3. And then, yeah, this is 2 minus 3 is minus 1. 6 minus minus 1 is 7. That's not what you expect. So how do you get associativity? Again, compiler generators also allow you to define the associativity of operations. But again, I think it's more elegant to do this here just a little bit differently. I mean, in the end, what we are generating here is a sequence of m plus or minus m plus or minus m plus or minus m. And there really is no reason why both of these sides should be e's, because that just gives us some ambiguity as to the order in which we generate them. You know, we could generate them like this, or we could generate them like this. You know, there's and that's just not necessary. We can instead just force the order in which these are generated by putting the m directly on the right-hand side. So we can have the m here, here, and here we put the x. And now if we generate this m plus m plus m plus m, then we are forced to have this last m in the last step. And yeah, this way we force the structure of the tree to be on this left side, and that's just the same thing as being left associative, right? Because the thing that we get from further down the tree is the stuff that's on the left side, and then we do the next thing on the right side to it. Okay, so that's how you can deal with associativity. Another tip that I want to give you, this identifier equals expression. If you are actually writing a programming language, don't do it like this, because yeah, for this primitive language that's okay. We only have variables identified by identifiers, but in a bigger programming language, when you have multiple different assignment operators like plus equal, minus equal, and so on, and then you start adding pointers and arrays, then this really gets out of hand. So do yourself a favor, and instead of using identifier here, have another non-terminal for L values, and then just start like L value goes to identifier. Yeah, and then later you can add stuff like identifier, open bracket, expression, close bracket, and stuff like that for arrays. You save yourself a lot of headache if you do this right from the start. All right. Now there is one more classical problem in compiler design that I want to address. That's called the dangling else problem. you see we have this if open B close S and if open B close S else S production rules. Now suppose if I had a source code like this, if A equals 0, I don't know, doesn't matter, then if B equals 0, I don't know, set P to 0, else set Q to 0. So normally programming languages handle this like this. If you have an else, it gets associated with the last open if. But if your production rules are like this, well, it would be completely legal to go from this S directly to the if open B close S else S. And then go from this else from this S to if open B close S. So that would effectively associate this else with the wrong if. Okay, and yeah, solving this is a bit annoying. It's a bit complicated. But yeah, I mean, compiler generators normally have facilities to address this problem. So you could just say, hey, I want this production rule to have a higher priority than this one. So that would just forbid making the mistake that I made down here. But yeah, I mean, there are compiler generators that don't have such facilities. And I think it's just cleaner to solve it directly in the grammar. But again, it's a bit annoying, so I won't blame you if you do it with compiler generator facilities. Okay, so if you want to solve this in the grammar, so you have to split these statement rules into two different kinds of statements, into incomplete statements and complete statements. Okay, and yeah, the incomplete statements, yeah, for example, if you have if open B close without an else, that's incomplete. Okay, because there could be an else after that, and that would mess with an else that would be on a higher level. So an incomplete statement could be if open B close S. Okay, and another way to be incomplete would be to have if open B close a complete statement, because before an else here you cannot have an incomplete statement. So we require here to be a complete statement, but after the else, if you have an incomplete statement there, then you are again also incomplete. And the same thing with loops while open B close incomplete statement. So if your while loop contains or ends with an incomplete statement here, then that while loop itself is also an incomplete statement. Okay, and a complete statement would be if open B close complete statement, else complete statement, or while open B close complete statement. Okay, so the thing is that if you end with an incomplete statement, then you're incomplete. If you end with a complete statement, you are complete, but not necessarily. So in this case, if open B close S, notice we can have any statement here, including a complete statement. But the thing is, if you don't have an else, then that already makes you incomplete. Okay, so that's why you can have an S here, but you're still incomplete. And that's why we don't have something like if open B close C. You know, just because you end with a C doesn't make you complete necessarily. Because this if open B close without an else would already make this statement incomplete. But notice between this close and else, we always require there to be a complete statement there, right? So that's the point where we say, okay, if we have an else ourselves, then in there we cannot allow an incomplete statement because that would break this else. And then there's also the case, like with the parentheses in arithmetic expressions. The parentheses of statements are the open braces, right? So open braces, T, so any number of statements, close braces. Yeah, if you have braces, well, then it doesn't matter what happens inside. These braces make a statement complete. You know, they delimit any statements in there sufficiently. And everything else like function calls and assignments like L equals expression semicolon or identifier open close, for example, semicolon, like function calls are also they are just complete because they are not missing anything. They wouldn't eat up an else after that. Okay, so normally everything is just a complete statement, and these incomplete statements are just some special cases that we need to deal with separately. Okay. Okay. Yeah. So I think that's enough for today. We've really discussed a lot of topics here, but we haven't even addressed the question how to turn this into a computer program. You know, but that's a pretty complicated topic. I will make another video about that, but it would just be too much to address it also today. So if you're interested in this topic, I have this book here, Hopcroft, Matwani and Ullman. This is a German book, but I think it also exists in English. That's a really good book. It's well written and very understandable, at least I thought so. I will put a link to that in the description, and full disclosure, if you buy that book through that link, I will get a little commission, but I don't even know how much, and I assure you I would not be recommending this book if I didn't really like it, if I hadn't read it and really thought it was a good book. You know, it's just that I figured if I'm gonna recommend a book anyway, then I might as well get a little commission. So whatever. Yeah, so as I said, next time we will talk about techniques to turn these things into computer programs. That's a bit a theoretical topic, but I find it very fascinating, so I wouldn't miss it if I were you, but again, quite theoretical. If you're not so into the theory behind it, you might not be so interested. But anyhow, if you like this video, like it, share it, subscribe, and see you next time.